In this video, we're going to look at a Tesla mechanical design engineer interview question. I really like to break problems down into smaller steps. It makes them seem more approachable to me. So we will do that in this video. The 4 steps we're going to take to solve today's problem are 1. Review the problem, 2. Identify the equations and cover our background topics, 3. Attempt our solution, and 4. Review the answer we came up with. Let's dive right in with step 1, reviewing today's problem. The problem we are dealing with states a hole in an aluminum plate machined of 6061 T6 is measured to be in spec between 25 millimeters and 25.1 millimeters at 25 degrees Celsius. A steel pin of 25.105 millimeters to 25.115 millimeters is thermally fit to the hole. How much must the plate be heated to ensure all pins can be installed? Room temperature is 25 degrees Celsius. The coefficient of thermal expansion of the plate is 25 microns per meter Kelvin. There are a few key pieces of info we want to take away from this problem statement, and they're also going to serve as hints guiding us towards the equation set that we will use. First off, we know our aluminum plate hole has allowable diameter limits between 25 millimeters and 25.1 millimeters. This means the maximum diameter of the hole is going to be 25.1 millimeters. Next, we know our steel pin is going to have limits of 25.105 millimeters and 25.115 millimeters. Additionally, we're told that room temperature is 25 degrees Celsius. Finally, the last critical bit of information in our problem states that our coefficient of thermal expansion is 25 microns per meter Kelvin. This serves as a big hint that we want to look up our thermal expansion equations. Now, this is a good time to move on to step 2, identifying the equations we want to use to solve this problem. As we now know, because the coefficient of thermal expansion is provided, we want to look up our thermal expansion equations. When we do this, we find our thermal expansion coefficient is equal to change in length divided by the original length times the change in temperature. Another way of writing this is the change in length is equal to the coefficient of thermal expansion times the change in temperature times the initial length. Or we can also write it as change in temperature equals the change in length divided by the initial length times the coefficient of thermal expansion. Now, this is the primary equation we're going to be using to solve today's problem. There's one other concept we should be familiar with, however, and that is the 3 types of shaft hole fits. The first type of fit is a clearance fit. This means that all possible dimensions of the pin fit within the hole it's being joined to. In other words, there's clearance for the fit. The second possible fit is a transition fit, meaning the dimensions of the pin joining the hole may or may not interfere with the hole. And lastly, there are interference fits. This means that all possible hole dimensions are smaller than the possible pin dimensions. For these types of fits, methods such as applying force or using thermal expansion are used to help fit the pin or shaft in the hole. This is the type of fit we are dealing with in this problem, as the maximum possible aluminum plate diameter is less than the minimum possible pin diameter. We use thermal expansion to ensure that we get the maximum possible plate diameter. Now that we know the equations we're working with and the types of shaft hole fits, we can move on to step 3, attempting our solution. Let's start by plugging what we know right into the third form of the thermal expansion equation we came up with. Change in temperature is equal to change in length divided by initial length times coefficient of thermal expansion. Doing this, we get final temperature minus 25 degrees Celsius, our initial temperature, is equal to 25.11 millimeters minus 25 millimeters, or the maximum amount our plate diameter changes within its tolerance, times 10 to the negative third to convert millimeters to meters, divided by our initial hole diameter. which is 25 times 10 to the negative third meters, divided by our coefficient of thermal expansion, which is 25 microns per meter Kelvin. Now, 1 micron is 10 to the negative 6 meters, so this is equivalent to 25 times 10 to the negative 6. Solving for our final temperature, we add 25 degrees Celsius to the right-hand side of our equation, and we find that the final temperature of the plate, such that we get the maximum hole diameter to allow for the easiest fit of our pin, is 185 degrees Celsius. Finally, let's move on to step 4, reviewing our answer. When solving our equation, you may be thinking we have an issue. The left-hand side of our equation deals with Celsius, and the right-hand side has units of Kelvin. However, because there's a constant offset between the change in temperature, regardless of whether we use Celsius or Kelvin, this unit discrepancy can be ignored. As a result, our final solution appears to be correct. There you have it, another Tesla Mechanical Design Engineer interview question solved. If you solved this problem differently or came up with another solution, please leave a comment below. Hope you enjoyed this video. Don't forget to like, comment, and subscribe.